All right, this is the most missed topic last year on the test. 80% of my students missed this last year. So I'm going to do a video and we're going to do a few of these to hopefully help you prepare for this topic. Make sure you practice this topic a lot in ALEKS and make sure you can do it consistently before you take the test. So this one is predicting the arrangement of electron groups around the central atom of a molecule. So we have this ion, IO4 minus. It's an anion, periodate. Let's go to our whiteboard. Okay, and the first thing that we need to do is we need to draw the Lewis structure. And we're going to count the electron groups. And then count. And then the last thing that we need to do is based on the number of electron groups, we're going to name the shape. Name the shape of the electron groups. Okay, so we need to draw the Lewis structure. So the first thing is we need to figure out how many valence electrons there are. So we have iodine. We need to figure out how many valence electrons that has, and then we have 4 oxygen. So how many does each oxygen have times 4? And then add that up. And we need to figure out the valence electrons by the periodic table. So we'll go back to ALEKS, and you get this on the test. So we need to figure out iodine. Iodine's over here. So remember, these columns are telling us how many valence electrons. So this column has 1, 2, 3, 4, 5, 6, 7, 8. So iodine is in this column. So iodine has 7 valence electrons. I'm going to write that down really quick. And then oxygen is in this column. It has 6. So I'm also going to write that down. Okay, so then, we are going to calculate the total valence electrons that we need to show in the structure. We care about valence electrons because those are the ones that bond. 6 times 4 is 24. Well, that's 24. 7 plus 7. And then remember, we have a minus sign. So remember that minus sign means that we get an extra electron. We have more negative than we started with the neutral. So let's just put that here. So that's from our negative charge. And then 8 plus 24, I guess I should write it like, let's make this a little less confusing. We're going to add the 1 electron here. There we go. Now 8 plus 24 is 32. Just make my math a little bit easier. So we have 32 electrons that we need to show in this Lewis structure. We are going to pick iodine as the central atom. I think this question also points out which element is the central atom, but because there's only one of them, that's going to be the central atom. So we're going to put iodine in the middle and then connect it to 4 oxygens. Okay. And remember, each bond is 2 electrons. 2, 4, 6, 8. So minus 8 gets us back to 24 electrons. So we have 24 electrons that we need to show here. Okay, so I'm going to start putting them on here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've shown all 24 valence electrons, and we have 0 left to show. So let's make sure everything has an octet. Oh, also we need to show the minus. This is an ion, not a neutral atom or molecule. Let's see. So this oxygen has 2, 4, 6, 8. Anytime there's a bond, each atom can see those electrons. This iodine has 2, 4, 6, 8. So everything has 8 valence electrons. The structure is happy. So that's our first thing. Then we're going to look at the electron groups around the central atom. So iodine is the central atom, and then anything touching iodine counts as an electron group. So we have 1 bond here, 2, 3, 4. So this has 4 electron groups. And then we need to use the chart or memorize, if we have a certain number of electron groups, what is the shape? So let's go back to ALEKS and type that in. So we have, in this structure, there are 4 valence electrons around the central iodine atom. That's 4. Okay, and then what phrase best describes the arrangement of these electron groups around the central iodine atom? So be really careful here. that chart in our notes, so this is in the module for chapter 4, we just care about the electron pair geometry. We don't care about the molecular geometry here. We're kind of ignoring lone pairs. We just care about those electron groups. It doesn't really matter here. But I would make sure that I put these 2 columns on my note card. Number of electron dense areas and electron pair geometry. So we have 4 electron groups in this periodate ion. And so that would make it a tetrahedral geometry. So let's go back to Alex and look for tetrahedral. Good thing we don't have to worry about spelling here. Okay, so we have 4 electron groups, and those electron groups, not the molecular geometry, make it tetrahedral. Okay, so we have to really be careful. Some of these questions say electron geometry and some say molecular geometry. So you need to really pay attention and read what it's asking, and then make sure you match it correctly to the correct shape. Let's do a few more of these. Again, this was the most missed question last year, and again, 80% of my students last year missed it, so make sure that you practice this one. Let me erase my board. This we have sulfur trioxide, so let me write that out, sulfur trioxide. And then while we're here, let's look at our periodic table. We need to figure out the number of valence electrons sulfur and oxygen have. Sulfur and oxygen both have 6. So I'm going to write that down. Sulfur has 6, oxygen has 6. So I'm first drawing the Lewis structure of this sulfur trioxide. All right, so, and there's 3 oxygens. Basically, we're taking 6 times 4. This would be 18 plus 6 gives us 24. So we have 24 valence electrons that we need to show here. So I'm going to draw sulfur, and then I'm going to connect it to 3 oxygens. So now we've got 2, 4, 6. We've shown 6 valence electrons. We have how many left? 18 left to show. So I'm going to start putting them around the oxygens. 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, well, now we've shown all of our valence electrons. We have none left to show. If we look at this oxygen, they're symmetrical, so I'm just going to look at this one. This oxygen has 2, 4, 6, 8 electrons. So its octet is satisfied. If we look at sulfur, though, sulfur only has 2, 4, 6. So the bonds each have 2, 2, 4, 6. So this sulfur is not happy. So what we're going to do is we're just going to pick some lone pair, and we're going to move that lone pair in between the atoms so that they're sharing those electrons. So that I'm going to draw that again. So I'm just going to copy everything down, but now we have a double bond over here. Okay, so now sulfur has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. 2, 4, 6, 8. So this is our structure, our Lewis structure. So the next thing that we need to do here is count the electron groups. So if it's a double bond, that only counts as 1 electron group. So I'm going to look at my central atom, sulfur, and I'm going to look at and see how many electron groups. So where are the electrons living? There's electrons living here. There's electrons living here. There's electrons living here. So this has only 3 electron groups. I think a misconception is that, oh, there's 2 bonds here. It's a double bond, but a double bond is a single type of bond. So it's only 1 bond. This is a double bond. 1 bond, 1 place for electrons to live. 2, 3. So there's 3 total electron groups around the sulfur. So then we need to go back to our chart and decide. Let's read the question again. Electron groups. So if we're talking about electron groups, we're going to look at the electron pair geometry. If there's 3 groups, then it's trigonal planar. So be really careful, make sure you match it very exactly. Remember, Alex is very picky. We have 3 electron groups around our central atom, and that is trigonal planar. Okay. All right. Let's practice another one. This one is difluoroiodide. And this one's an anion, so we're going to watch for that. So I'm going to write this down. We've got F2 minus. And we need to know how many valence electrons iodine and fluorine have. And they're both in this column. That's 7 valence electrons. And then remember we have a minus charge. So let's go back to our board. So remember the minus means we get to add one more electron. Oops. Okay, so 7 times 2 is 14 plus 7 is 21. Then we have one more from this minus. So we've got 22 electrons that we need to show in this structure. I'm going to pick iodine as a central atom because there's only one of them. The other thing we can look at is if it's electronegative. The greater the electronegativity, generally, that's not going to be central. So lower electronegativity likes to be in the middle, generally. All right, so I'm just going to put the fluorines on opposite sides. So I've just used 2 4 electrons. So 22 minus 14, we're back down to 18 electrons. And then I'm going to start filling them around the fluorines to fill up the octets. So 2, 4, 6, 8, 10, 12. I just used 12 electrons up. Now I have 6 electrons left. Oops, my marker. And the fluorine has 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. So that's full. Now we'll fill up the octet around iodine. So iodine right now has 2, 4. So we're going to put 2, 4. We've used up 4 more electrons. We've still got 2 left to show in the structure. So this is a kind of a weird one because the fluorines have 8. The iodine has 8. Well, what we can do is we can put more lone pairs on the central atom. So that's what I'm going to do. I'm going to put this extra 2 electrons as a lone pair on the central atom. Now, I've shown all of my valence electrons. So, iodine, this is kind of uncomfortable because we've been talking about the octet rule and all of a sudden we put extra electrons on iodine. So we've got 2, 4, 6, 8, 10. Now iodine has 10 electrons. There is a rule that says if the atom is below the 3rd row, if it's in the 3rd row or below, it can fit more than an octet. So, and this happens, this is not just made up, this is based on experiment. We've observed this. So iodine is a pretty big atom. It can fit more than just 8 valence electrons around it. And so that's where we will put the extra electrons on the central atom. Okay, so now that we have our structure, we're going to count the electron domains, the number of electron groups around the central atom. So I have a lone pair counts as 1. Here's another lone pair. Here's a bond. Here's another bond. Here's a lone pair. So we've got 1, 2, oops, let's not make that look like an electron. 1, 2, 3, 4, 5. So here we have 5 electron groups. So let's go back to our Alex. So we have 5 electron groups here. And then if we have, let's see, what phrase best describes the arrangement of these electron groups? So be really careful. It says electron groups. If it says electron groups, we're using the electron pair geometry, and we just have to use these 2 columns. So 5 electron groups, we have trigonal bipyramidal. So be really careful, make sure you match it exactly. There is a trigonal bipyramidal down here at the bottom. Trigonal bipyramidal because there's 5 electron groups. Okay, let's keep practicing. Oops, there. Okay, this one is weird. We have cyanate. And it's an anion, so we're going to add electrons. And it tells us carbon is central. Okay, carbon is not, or the central atom in the formula is not always the central atom, so be really careful. So we have OCN. And let's see, we have oxygen has 6, brings us 6 valence electrons. Carbon brings us 4 valence electrons. Nitrogen brings us 5 valence electrons. And then our minus charge brings us 1. This probably makes more sense if I wrote it like this. Let me pull up my... Okay, so this is the total. We've got 10 plus 6. We've got 16 valence electrons that we need to show. And it said carbon central, so let's put it in the center. And if it's in the center, it has to be connected to the other atoms. And so far we've used 2 4 electrons. And then we have 12 left to show. So let's start by putting them around 2, 4, 6, 8, 10, 12. Okay, well, looks good. For the exterior atoms, the outside atoms, we've got 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. But carbon only has 2, 4, so we need to fix this. So what we're going to do is, let's see. Let's just bring 2 from each side. I'll bring 2 down from each element, and we'll redraw. So we've got carbon with a double bond here, and carbon with a double bond here. That's one pair. So now we've got, around carbon, we've got 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8. The nitrogen has 2, 4, 6, 8. So everything has an octet. Everything wants one. Oh, remember, this is an anion, so we need to show that it's an anion. And then we need to count the electron groups around the central atom. So carbon central. And then remember, a double bond, this is only one place where the electrons can live. So this is a bond, this is a bond. So this only has 2 electron groups. So let's go back to our Alex. This has 2 electron groups, and then it says, what phrase best describes the arrangement of these electron groups? So we just care about the electrons. We don't care if there's lone pairs. There's not on the central atom. If there's 2 electron dense areas, like in our molecule, this is linear. So then we just have to do the pull down. This is linear. Okay. Let's do one more. Let's see. Did we do this one? We haven't done this one. Okay, let's try this one. This will be our last one. So we have pentafluoride, iodine pentafluoride. So IF5. My marker is losing ink. Okay, and then remember we need to look at how many valence electrons. Go to the periodic table. Iodine has 7. Fluorine also has 7. Fluorine, there's 5 fluorine, so that's 7 times 5 is 35 plus 7, 42. That makes sense. 7 times 6 is 42. Okay, so we're going to pick iodine as our central atom. And then we're going to, right off the bat, we have 5 groups. And that's okay, because we talked about this. Iodine is a big atom. It can accommodate a lot of electrons. So first put them around, let's see, 2, 4, 6, 8, 10. We've used 10 electrons already, so we've got 32 left to show. And then we'll go ahead and put these electrons around these groups. So let's go ahead and do that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. What's after 26? 28, 30. So we've just used 30 electrons. We have 2 valence electrons left to show. So I've put 6 around each fluorine so that now they have the bond, and then 6 in their lone pairs, the 6 electrons. So we've got 2, 4, 6, 8. So each of the fluorines has 8 electrons, so it has a satisfied octet. Iodine has 2, 4, 6, 8, 10, and we're going to put 2 more around it because it can fit more. It's big. It can fit a lot of electrons around it. And we have to show these electrons. So now we've shown those. So now let's go ahead and count the electron groups around a central atom. So we have a lone pair that counts as 1. We have 1, 2, 3, 4, 5 bonds and a lone pair. This has 6 electron groups. So now we'll go back to Alex and use our electron geometry sheet. So this has 6 valence electrons, or excuse me, 6 electron groups, and then let's read this. It says, what phrase best describes the arrangement of these electron groups? If it's talking about electron groups, then we're just using this column, electron groups. We don't care about the lone pairs. So this one, because it has 6 electron groups, it's going to be octahedral. So let's go back here and find octahedral. Okay, if this one asked about molecular geometry, so if it's saying what is the shape of the molecule, then you need to be more careful and you need to use this molecular geometry. And so this one, if we go back to our picture, we have 5 bonds and 1 lone pair. So if we go back to our sheet, we're looking for 6, still 6 electron groups, but 5 of those are bonds, 1 is a lone pair. This would be square pyramidal. So that's how we do that with this. We just we have 6 electron domains and then we count how many lone pairs. And that's if we're looking at molecular geometry, the shape of the molecule. We're ignoring the lone pair. If we're just looking at electron pair geometry, then we just use this first column.